In our last video, we learned about the law of sines. Essentially, we learned that if you have an oblique triangle, ABC, with sides little a, little b, and little c, that there is a proportionality across the triangle between the sine of each angle and its corresponding side. In that video, we also came up with a proof of the law of sines that involved dropping an altitude, call it h, and that altitude allowed us to connect angle A, and angle B to side A and side B just using plain old SOHCAHTOA involving the sine ratio. And that proof seemed pretty good. However, it had one big flaw. It made an assumption that the oblique triangle that we were dealing with was acute, or at the very least that the angle here at A and the angle here at B were both acute angles, so that the altitude was measured on the inside of the triangle. What I'd like to do to start this video is show you a proof of the obtuse case. Last video showed the proof of the acute case. So the obtuse case of the law of sines starts with an oblique triangle, but it'll look like maybe this instead, where you'll have somewhere on the base an obtuse angle. So I'll just call A my obtuse angle, and I'll call this triangle A, B, C. And I'll label the sides little a, little b, and little c right here. So once again, I want to draw an altitude, but I'm going to draw the altitude from B. Now the altitude from B, as you can see here, doing that wrong, let's try that again. The altitude from B here would be on the outside of the triangle. And it would meet AC, if you were to extend it, somewhere on the exterior of the triangle. So I'll call that altitude H. Okay. So what I can say now, looking at this triangle, I only have, I have two right triangles. I have right triangle, if I call this point over here maybe X. I have a right triangle CXB, and I have right triangle AXB. So what I can say is I can write two sine ratios using those right triangles. I could write that sine of C is equal to H over A. That sounds great. Sounds very familiar to the last time, so that H is equal to A sine C. However, I can't say anything directly about the sine of A. You see, sine of A is the angle in here, right? I can't say anything directly about its sine and how it relates to H, because that's not part of the right triangle. However, you'll notice that this angle, BAX, is the supplement of angle A in the original triangle. So that's 180 minus A. So I can say that sine, let's get the color right here, the sine of 180 minus A is equal to H over C. So that H is equal to C times sine of 180 minus A. And when I connect these two statements by eliminating the H, I get that A sine C is equal to C sine of 180 minus A. And when I write it as maybe a more natural proportion, it would look like this. Sine of C over C equals sine of 180 minus A over A. Okay, so that's the obtuse case of the law of sines. And of course, you can go and you connect it to sine of B over B by drawing a different altitude, or turning the triangle on its side even. Well, one thing you should note, though, is we know this rule about sine. We know that when I'm looking at sine of 180 minus a, that is one and the same as sine of a. So I can actually just take the obtuse case proof one step further and replace sine of 180 minus a with sine of a over a, and I could do the same thing with sine of b over b. So what we see is that the obtuse case actually works out just the same, all because we had that nice little rule way back when that sine of theta is equal to sine of 180 minus theta. And if you don't remember that rule, maybe you just challenge yourself to check that it's true using sine's difference identity. That's a nice thing about those difference identities. This is like if you forget different rules, you can punch them in and see that things work out. So that actually means two things. That means the law of sines works for oblique triangles with three acute angles, and it also works for oblique triangles with three obtuse angles. But one little catch there, one thing you want to keep in mind, and that's when you're using law of sines to solve for an angle. I'm going to put this right down here as a little warning. Warning. We're going to see more of this soon. When we are using law of sines to find, by find I mean I got to solve for an obtuse angle, you need to beware. And that's because sine inverse of any value that you put in will only return an acute angle. It'll only return the supplement if you're looking for the obtuse. So maybe you do sine inverse and you figure out that the angle's 60 degrees, but you know it should be obtuse. And you say, okay, the angle I found was like the 60-degree angle over here. I need 120 degrees. I need its supplement. And one way that you can always check yourself to avoid errors is you should make sure that the largest angle is always across from the largest side, just like that. Okay, one other thing that I want to achieve in this video, and it's a little bit different, is I want to introduce you to using law of sines and cosines to solve a word problem. That's probably the most common thing that you'll be doing. So here's a big block of text. So we'll read through this. And this word problem doesn't have any kind of a diagram along with it. A lot of times, especially in the beginning, you'll get word problems with a nice little diagram there, so it's not too challenging, and sometimes you don't even have to read the words. But I think it's really important to be able to take a word problem without any kind of diagram and read through it and make you form a picture in your head. Kind of take the story and try to act it out in such a way that you can understand what's going on. You can turn it into math, and then you can solve it. So here we are. This one is a little wacky. Suppose you lived on the 5th floor of a tall apartment building. You don't know anyone else in your building, but you have 2 friends in the building across the street. One of your friends lives way up near the top floor, and the other lives down near the bottom floor, and they're approximately 100 feet apart from each other. Their apartments face yours so that when you look out the window and they look out the window, you can wave and see each other. Okay, let's stop there and start to try to draw. So we've got a tall apartment building here and another tall apartment building over here. They're not necessarily the same height, but maybe they are. And what we know is you have a place right about here, maybe, on the 5th floor. I'm guessing that's somewhere in the middle. And then you have a friend way up near the top and another friend down near the bottom. And we know that they are 100 feet apart from each other. And we know that when we all look out the windows, we can see each other and wave, or you can see each other and wave. Okay, what's next? It says the 3 of you, feeling socially isolated, decide to order a set of walkie-talkies so that you can communicate. The range of the walkie-talkies is advertised as more than 100 feet. So your friends will be able to communicate with each other, but you aren't sure if you'll be able to join in the fun. So you create a makeshift clinometer. A clinometer is a little device that measures angles. And you measure the angle of elevation to your lofty friend, that's the one up top, as 56 degrees. So an angle of elevation, it's a common term in these problems. You'll probably see it again. Basically, the angle of elevation from you to your lofty friend, and an angle of elevation is always looking up. It's measured from the horizontal. So I have to picture the horizontal here, where you would be looking if you look directly at the building. And then if you raise your line of sight until you're looking directly at your friend at the top there, that's the angle of elevation that we're talking about here, elevation. And that is said to be 56 degrees. Okay. And next we see another angle, the angle of depression. That's kind of a sad choice of terms there. But an angle of depression is also measured from the horizontal. So there it is again. But it must be looking down. You'll see those terms again. Elevation and depression. So the angle of depression means looking down from the horizontal. And that angle is 23 degrees. Okay, so the question is, will you be able to join in the conversation? So we did all this work, and essentially we just got this triangle, and I'm just going to redraw it right down here for a second so you can kind of picture it again. And what we know about that triangle is we know that one side is 100, and we know that the angle across from it is 56 and 23, which makes 79 degrees. 79 degrees. So when I draw it like that, it actually doesn't seem like I have enough information to solve the triangle. I have enough information to write an angle-side pair ratio, like you would need in the law of sines, sine of 79 over 100, but it doesn't appear that I have either of the missing angles or either of the missing sides. And the missing sides, let's just call them x and y, are precisely what I need to know, what I'm asked to find. Am I able to join in the conversation? I could try to reason about this a little bit and say, well, if 100 is the side across from a 79-degree angle, as long as the two angles at the bases here are both less than 79 degrees, which they could be, then that would imply that both x and y would be less than 100, and we would be in good shape. But we actually can do better than that. Because if I look at my original picture here, and I had this blue triangle, that was a right triangle. So I knew that this angle up here in the corner was 180 minus 90 minus 56. So that was a 34-degree angle. Meanwhile, down in the green triangle, I had a 57-degree triangle. 57 and 23 only makes 80. That makes that a 67-degree triangle. So if I now go back to this picture here, I can say that this is 34 degrees and this is 67 degrees. And I actually do now. I have enough information to solve for x and y. I could just punch them in like this. It would be sine of 67 over x, and I could work out x. And then I could write the ratio again. Sine of 79 over 100 equals sine of 34 over y, and I could work out y. And that's how you can use law of sines to solve a word problem. Over the next couple days, you'll get used to solving word problems where you have diagrams and word problems where you don't. One last thing to think about here. Suppose for a second that your two friends actually weren't quite sure that they were 100 feet apart. That you did actually know the measurement of x here, and you knew the measurement of y, but we didn't have any other information other than x, y, and 79 degrees. So all this information, on your friend's side of the world was all missing. All I had was a length on one side of the triangle, an angle, and a length on the other side of the triangle. That's what we would call a side angle side relationship. Like maybe x was 90 and y was 80, and then the angle was 79 degrees. Could you solve that with the law of sines? That's something I want you to think about before you play the next video.